Hey guys, welcome to another video. So today we continue the topic of binomial theorem proving identities, where in the last video we introduced the framework and most importantly the formula that we use, which is Newton's formula, where we sub in, instead of A and B, we use 1 and X. So I guess last lesson, I went on a bit of a rant, right? And the rant was basically, I'm not happy that a lot of teachers following the NESA guidelines and the NESA proposed syllabus do binomial theorem proving identities. They do it in year 11 before they do calculus and before they do differentiation, or they've done differentiation but haven't done integration. It's disappointing because there are questions, as you'll see today, that uses calculus, right? Uses integration and differentiation that they can't do in year 11. So what happens is at those schools, they do it twice, right? They do binomial theorem in year 11 and then binomial theorem in year 12. Why split it where that is only the key difference, right? It doesn't make sense. So today, anyway, we will do questions using differentiation and integration. So by the end of year 12, for those that have seen this in year 11, you will see questions that look like this. So let's do this. Binomial theorem. And if you haven't already done so, please subscribe to the channel, share the video. It just helps with the searching algorithm that they use on YouTube. These videos are free, no strings attached. Just share it with your friends. Yeah, helps with the searches. So proving identities. All right, so Newton's formula with 1 and X subbed in, right, is really useful in that it basically gives you a generic expansion of a polynomial, right? Where the first coefficient is NC0, all the coefficients are combinatoric terms, NC1, x to the power 1, NC2, x squared, plus all the way to NCn, xn, right? That was all covered in the last lesson. And today we basically apply calculus to this. So, there really isn't much more theory than for me to now dive into an example that showcases the differentiation and the integration type question, and then 2 past papers. Pretty simple. So maybe in this one I can just fit the question right under here. So oops, example. So by considering the expansion of 1 plus x to the power of n, show. Now, most questions that you see in past papers, trial papers, and the HSC, they have the next part here as part A, and then if it's a cool question, there's a part B that makes you think about using part A and other things that you know as well. So let's go there in a sec, but let's do this one. First one, prove this, NC1 plus 2NC2 plus 3NC3 plus NCn equals to n times 2 to the power n minus 1. Yep, classic. And then B 1 plus C0 x1. No x's. Sorry, it's only been C0. Half NC1 plus third NC2 plus C3 1 on plus 1 Cn equals 2 to the power of n plus 1 plus 1 over plus 1. All right. Now, these 2 questions can't be more textbook, right? When you apply calculus today. So just for labeling purposes, absolutely. Now, what I always ask my classes to sort of find, right, in these questions is little subtle hints that tell you whether you're using calculus or not. Look at this, right? One thing to note is, like when you differentiate x to the power of n, or x squared or x cubed, right? What happens is the power comes down and you minus 1 to the power. That power coming down here, when you differentiate, is actually the biggest driver of process leak. Look at this, right? See all these numbers in front? How did they get there? You've differentiated it. right? You've differentiated every term with x in the formula here, right? All these powers of x get differentiated, all those powers come down, and you get that expression down there. So I say to my class, if you see whole numbers in particular get multiplied by the combinatoric terms, you're going to differentiate. By the same token, when you integrate, right, x to the power of 5, right, what you do is you add 1 to the power and you divide by that new higher power, right? So if it was x to the power of 5, you divide by 6. That's why if you look at these, sorry, I use highlighter, these fractions here, it's like dividing, yeah, it's like integrating these powers here, adding 1 to the power and then dividing. That's why for the NC2, this guy here, there's 1 on 3 because you've added 1 to the power. So whenever you see fractions, firstly, and secondly, the number on the bottom of that fraction is 1 higher than the combinatoric term, then that sort of gives you a good clue that it might be integration. So just to be clear here, this one is differentiation. This one's integration, right? Just those little subtle hints that are absolutely key for this. Now, when you have that foundational inkling to whether it's differentiation or integration, it then guides you for the harder questions that look a bit more, look a bit less obvious. It guides you into using one or the other, right? This gives you like another technique. So let's do part A. So really easy, right? Once you know, guys. What I'm going to do for both of these questions, I'm going to state that this original expansion of 1 plus x to the power of n, let's call that number 1, right? Because everything stems from there. And I'm going to switch the side. So the 1 plus x to the power of n, I'll put it on the right-hand side. So I'm just going to say, step 1, differentiate. Now let's be clear with respect to x, number 1. Right? So differentiate that with respect to x. So then you get, now let's do the right-hand side. So let's do this side first. We know that this guy's a constant. When you differentiate, it goes away. This guy's x to the power of 1. So when you differentiate, only the constant remains. Plus now, this guy differentiated, the 2 will come down, multiply by that. Plus now, there is an invisible term here. So in the dot, dot, dots, x cubed. So let's actually write that down. So the 3 comes down, NC 3x2, right? Minus 1 to the power plus. Now what happens to the NCN term? The n comes down, multiplies with NCN, and minus 1 to the power. So it becomes n times NCN x n minus 1, right? That is the derivative of the polynomial expression. For the binomial on the other side, guys, we're going to apply the chain rule here, right? Where I take the power down, minus 1 to the power of that expression, that function, and then multiply that by technically the derivative of the inside, which is 1. Yeah, that's the chain rule. Yeah. All right, almost there. So I'm just gonna now at this point sort of remove the times 1. Don't need it. Now you can see that looks very similar to what I want to prove. What I want to prove looks like that. And then, like last week, like I always say to my students, what next? What do I have in the thing I need to prove? Sorry, rather the opposite. What don't I have in the thing I want to prove that I currently still have in the black line there? There's no x's. X's are gone. Now, how do you make x disappear in mass in this context? You let x be 1, right? So once you do that, once you differentiate, call that number 2, and then all you got to do, quite simply, sub x equals 1 into 2, and you got it, right? It is that easy, right? Because if all of these terms here, that guy, that guy, that guy, this guy, all become 1s, you've got exactly what you wanted. Actually, I differentiated this guy incorrectly. Minus 1, that's better, right? So let's go. Sub x equals 1. Now show the substitution. Yeah, your teacher loves it when they do that, or when you do that. So it gives them a bit of comfort that you just didn't pluck something from air, right? Cn 1 to the power of n minus 1, n 1 plus 1, n minus 1, and then guys, we got it. NC1 plus 2NC2 plus 3NC3. All the 1s go away, right? So that's just n. And 1 plus 1 is 2 power of n. Boom. Very straightforward, isn't it? Now, once again, how do you know, right? That is always a question you need to ask yourself, because there's whole numbers in front of the combinatoric terms, right? That is the biggest giveaway. Similarly, in the next question, whenever you see fractions where it's escalating whole numbers, right, by 1, 2, 3, integration, right? So let's go there. So let me see how much space I have. I don't have a lot. So what I'm going to do, it's okay, I will copy this, plug it into the next one. Perfect, and I will do number 2, yeah, because I still need the binomial expansion there anyway. So part B, just like before, I'm going to now integrate. Yeah, number 1, I guess with respect to x or dx, right? So once again, let's flip the order. Now, integrating this, that's a constant, so I add x to it, right? So step 1 there, nc0x plus this one here, add 1 to the power of x, divide by new power x. So in line with what I'm seeing here, instead of dividing it by, I'll go n, actually, no, I'll divide it and I'll take it out just to clean that message up. So add 1 to the power, divide by new power. Now this guy's turn, add 1 to the power, divide by new power, plus, now they want me to do one more, so let's do one more. So once again, I really should have put in that cubic term, but nc3, add 1 to the power, divide by new power, plus dot, dot, dot. Now for the ncn, xn, I'm going to add 1 to the power. So the constant stays to add 1 to the power, divide by new power, all right? Now, we know that when I integrate and there's no limits, I need to add c, right? The constant for this guy. See how there's all these terms that I'm integrating. There's yeah, and there's both sides. There's constants on both sides. So what I'm going to do is just merge to one constant, right? So you don't need to put plus c's to any of these. Oh, so sorry, to all of these. You just need 1 plus c, and let's just do it on the right-hand side. So equals 2. Guys, I need to integrate this guy with respect to dx, right? So that's the function rule, the first sort of formula you get on your reference paper, where that's a function of power of n. Now the derivative of the inside is 1, so it's there. So quite simply, I can just add 1 to the power, right? I go 1 plus x to the power of n plus 1, divide by that new power, and then all important plus c. Yeah, and that's the constant I need to find now. So step 1, differentiated, right? Step 2, I now need to find this constant. How do I find this constant? I'm going to sub in a number that helps me do it. Now, what's a logical substitution? Sub in x, because when you sub in x, everything on this side goes away. And then you should be able to make the constant the subject. So showing full working out, let's call this number 2. Not that I need to really, but sub x equals 0 into 2. Yeah. So guys, zeros to everything. Can I, well, for this purpose, can I just go, if these are all zeros, let's just go, yeah, shortcut our working out. 0 on this side equals to, now, if I sub 0, let's see, right? If I sub 0 into here, right? This guy just becomes 1, doesn't it? 1, so 1 to the power of anything is 1, n plus 1 plus c. Therefore, this gives me c equals to negative 1 on n plus 1. Right? And then I'm going to sub this back into this guy here to get the expression, right? So maybe I'll go, therefore, nc0x. So I'm just, you know what? I've got PowerPoint, don't I? I can actually do this. Oh, I do miss this. I do miss this so much. Therefore, sorry, I don't know why there's random 2. There's a colon that sort of followed in the copy. Yeah, therefore, and then instead of c, we basically replace c with minus 1 on n plus 1. All right. Two things. 1, can you see that the denominator for the right-hand side is the same? So we're going to combine the two. Also, can you see in the thing we need to prove there are no x's? What have they done? Sub in x equals 1 again. So what I'm going to do, right? 2 things. Firstly, let's combine the common denominator and also call this number 3, and then go sub x equals to 1 into number 3, and we got it, all right? We got it because all the x's will go away, and we should get the term on the right-hand side looking like what we need, right, in the question above. So that should be proven. So once you do that, I got, so straight copy and paste. Let's just, once again, let's just be, love PowerPoint. Okay, let's see. So instead of x's though, we are going to drop in values of 1. You know what? No, I'm not going to be lazy because I'm also going to change it into the fraction term. So let's just write it out. So NC0 times 1 plus, now instead of on 2, on 3, on 4, I'm going to turn it into the fraction form. So it looks like the thing that I want to prove, right? Yeah, 1 on 3, NC2, 1 cubed plus 1 on 4, NC3, 1 to the power of 4 plus dot dot dot, 1 on n plus 1, NCn, 1 to the power of n plus 1. And then, like I said, on this side, common denominator is achieved. Now, all the 1s go away, but not only that, we know that NC0 specifically is 1, right? Anything C0 is 1. So, and the reason why that's important is because if you look at the thing I need to prove, the first term is 1, right? So what they've done is they've subbed in the combinatoric term of 1. 1 times 1 is 1. And I've proven what I needed to prove because all the 1 with brackets go away, right? C2 for NC3, last term on the left, NC, and that, oh, I didn't sub in, that's naughty. So let's do that now, sub in 1 there, because if it's 1, it is exactly what I want on the right hand side. So 2 to the power of n plus 1 minus 1 on plus 1. So that's it. Integration, that's how you do it, and that's how you know, because of the fractions that escalate by 1 or go up by 1, it's a very good sign. Now, if you're also on top of your game, you can also see on the right hand side, if the power sort of went down by 1, generally it's differentiation. If the power goes up by 1, generally it's integration, right? All right, that's the framework for doing calculus-related proving of identities in binomial theorem. Let's explore 2 questions, right? 2 questions. So this was from Ruse, right? Back in 2008. Now, when you look at this question, there's nothing really that indicates, oh, sorry, it's not obvious off the bat that it's differentiation, because the first one here basically just says, can you please expand? Write down the expansion of that, okay? Now, interesting here, there's a minus, right? Normally there's a plus and also 2 to the power of n, right? Which means it's even, which usually follows because it's telling you even. When there's a minus, by telling you it's even, it means that the last term that you expand is positive, right? Interesting. Now, how do you know it's differentiation? Look at it, right? And what did I say before? What's the clue that guides you to differentiation? Look at the numbers in front of the combinatorics, right? 3, 2, 4, right? There's all these numbers in front, right? How did they get there? Generally, they're done by differentiation. Not the only way, but if it increases, it's generally differentiation. But what's really important for this question is, why are there terms, expansion terms on both sides, right? Generally, when that happens, and can you see on both sides that every term is positive? So what they've done is, and it's especially important because this term has a negative x there, what they've done is, when they were on the one side, all the odd ones were positive and all the even ones were negative. And then they moved the even ones over to the other side to basically get the answer. So I guess what I'm trying to say is that we're just going to prove this with alternating odds and evens first, and then move the negatives on the other side, and you'll get what you want, right? So this question feels like the game plan is part 1, we're just going to expand, and then we're going to, for part 2, the game plan is differentiate, get rid of x, move any negatives to the other side, and we should be sweet. Let's have a look, right? Let's have a look. Part 1, let's attack this by going 1 minus x. Now, we know when it's 1 plus x, right? It's combinatoric term. Now, in this case, it used to be n, but because it's 2n, 2n c0 plus 2n c1. Now, c1, this term here, so I'll put with brackets minus x to the power of 1 plus 2n c2 minus x to the power of 2, 2n c3 minus x to the power of 3. All right, that's enough for us to develop a pattern, and 2n c2n. Now, this is important that when I go minus x to the power of 2n later, that's going to be a positive term, right? That's going to be a positive term. Now, so once you do all that, what we're going to do is basically, you can see with these negative x's, every time, right? Every time it's even, the last term included, they're positive. And every time it's odd, right? Negative x to the power of 1, negative x to the power of 3, they're negative, right? So then I know that, therefore, this guy expands to, NC0, oh, sorry, 2NC0 minus 2NC1x plus, so alternate 2NC2x squared minus 2NC3x cubed plus, and then the last term, right, we know it's even. How do I know it's even? Because it's 2 times any integer, right? If it's even, then the power of negative x makes it positive, right? So 2n c2n x 2n. Now, feels like I'm going to use this, so feels like I should name it number 1. Yeah? All right. So let's go down this path of saying differentiate to get the sort of coefficients in front. And then we sub in a number for x and see where that takes us, right? So I'm going to reverse the order again and say differentiate. Number 1. Yep. So let's do the now when you differentiate, the first term goes away, x, so that guy's gone, right? Differentiate this term, the x goes away, so you get minus 2nc1 first, and then this guy, the 2 comes down, plus 2nc2x. Now this term odd, the 3 comes down, minus 3 2nc3x squared plus ... Last term here, 2n comes down, and then 2nc2n x 2n minus 1, right? Equals to now. So that's the right hand side. This guy differentiated, remember, chain rule, right? So 2n comes down, minus 1 to the power, and then multiply by derivative of the inside, right? Which is important. Now, at this point, say to yourself, right, you know exactly what's going on here, because what you're going to do next is, by nature of not having any x's in there, they've subbed in x equals to 1 or negative 1. Generally, they're the choices. Feels like I should sub in 1 to everything. Like, and by everything, I mean like every time you see an x, there, and there. If I sub in 1, this is nice because this whole term, 1 minus this whole term goes away, right? That side 0. This side has positive and negatives, and then moving the negatives over, boom, you have exactly what you want. So we're almost there. So let's call this number M2. And I'm just going to say sub x equals to 1 into 2, right? So this side, let's see what we get. That guy. So show the substitution, right? So every time you see an x, replace it with a 1. Last term there is positive. That's nice. This side is crucial. 2n times 1 minus 1. 2n now. This isn't times negative 1. Doesn't matter because that whole term is 0, right? This whole term equals 0, right? So what do I have? So minus 2n. Now I'm freestyling. Oh, I also note that the combinatoric term that I did isn't this 2nc thing that you use the brackets. Let's do that now. So each time you see a combinatoric term, so 2nc1, just replace it with 2n1 like that, plus 2 times, and the ones all go away, right? Minus 3, 2nc3. You know what? I'm just going to add a few extra terms just so I can get the extra terms as a plus 4, 2nc4 minus dot dot dot. So what they've also done, you can see that they put in the second last term as well, which is definitely a negative, right? Because it's the last one's even, then the second last one's odd. The 2n minus 1. Sorry, I'm squashing this. Let's move it down a bit. And then 2n minus 1, and plus 2n times 2n, 0. All I've done there is basically removed all the ones, re-express the combinatoric terms, and set this guy to 0, right? And added in sort of a few terms in the dot dot dot. Yeah, guys, we're done, right? Because then all they've done, if you look at what they want to prove, let's see how they've done it. Don't know why they put the odd ones on this side, but if I move all the odd ones all over to the other side, boom, I have it, right? So I'm just going to say, therefore, right? Let's just move all the other ones on the other side and then assume that we flipped it. So all the other ones becomes positive as well. Plus, now the highest odd number is the second last term. So just to be clear, you know, that guy's there, even, and odd. And right now I'm writing all the odd ones, right? Was it all got a plus because I've moved it to the other side, right? And green. Done. How's that? Yeah, pretty sweet. Now, that's how you do a differentiation question, right? How do you know, once again, how do you know the whole number in front? That's the giveaway. That's really the tell, right? The tell sign there. I'm going to do one more, right? But for the next one from Helston 2018, I'm going to shortcut it in that part 1, can't believe it's worth 3 marks. That is the exact same question as the integration proof. I'm not going to do it, right? Where you refer back to a few slides before. So once again, they've given us, sorry, let's use pink. They've given us the classic binomial expansion. They've asked us to prove that, right? Let's assume that we have. Look at the next one. Oh, by the way, just be clear, how do we know it's integration? Well, it says integration, right? But also how do you know? Because the fractions on the bottom are escalating or increasing by 1s, right? That's a big giveaway. Now, I like the next question. I like it. You look at the next one, right? Look at the fractions. There's some interesting things happening there, right? The first fraction is a half, but not only that, it looks like it starts with the combinatoric term of NC1, right? Where's NC0? And here, the thing that I proved up to, it's gone, right? It's gone. NC0 is gone. And look at all these fractions, 2 on 3, 3 on 4. Now, I've just proved upstairs, 1 on 2, 1 on 3, right? It's unclear to me how the fractions appear like that. Now, this is key, right? This is absolutely key. First question is, why is there no NC0? That's gone, right? How do you eliminate a term? And elimination is actually a key word here. How do you eliminate? Where have you heard elimination before? Simultaneous equations. Now, with simultaneous equations, generally I have 2 equations and I minus to eliminate. Look at this. If I take number 1 minus number 2, this guy goes away, right? Yeah. And then if you look at n1, the whole number in front of there right now is 1. 1 minus a half gets me a half. If you look at the number in front of here, once I sub in x equals 1, that goes away. N on 2, there's a whole version of that. Minus a third gets me 2/3. Huh. That's the giveaway. So that's actually the punchline for this question. What they've done is they started with number 1, subbed in 1, right? Subbed in 1 is as x, so you get the expression that you want. And then they subtracted equation number 2 to basically eliminate to get what you want. Wow, right? So in this question, the next level of thinking is, how do I use what I've proven for integration? How do I use those fractions of 1 on 2, 1 on 3 to get the fractions of 1 on 2, 2 on 3, 3 on 4? Oh, they've taken the original, which is a whole number for each, and they subtracted these fractions. So what I'm going to do, I can't use this yet because I need to sub in x equals 1. So for part 2, a smart thing to start with is sub in x equals to 1 into number 1, right? And we know what we're going to get, all the coefficients. Let's just go there, right? So okay, n0 plus n1 plus n2 plus n3. I want n3 to sort of showcase the calculation. If you sub x equals 1 into the right hand side, 1 plus 1. Yep, let's call this number 3. Now, since, and I'm just going to copy and paste this because I want to line it up, right? Since 0 plus I want to line it up so nicely that it's very easy to visualize. Yeah, everything's lined up quite nicely. Yep, so this was number 2, right? You can see if I take number 3 now minus number 1, right? Vertically, right? It's stacked nicely, right? Vertically, these guys minus out. So let's do it. All right, let's do it. 3 minus 2, right? What do I get? Firstly, this guy eliminated, right? Secondly, this guy and this guy, right? A full version of this minus half version of this gets me a half version of this. Plus full version of this minus a third of this gets me 2/3 of that. Oh, perfect, right? Perfect. And then a full version of this minus a quarter of this gets me 3/4 of that. Yeah, so nice of a question. This one here, right? I got full version of this minus 1 of this. Now, the fraction of 1 minus 1 on n plus 1, common denominator, n plus 1 minus 1, n plus 1, n on n plus 1. Exactly the fraction that I want. N on n plus 1, n. Right? I have exactly what I want on the left. Now, on this side, it'll be 2 to the power of n minus 2n plus 1 minus 1. I'm almost there, right? I just got to clean up the algebra on the right, maybe common denominator that. Almost there. So 2 to the power of n plus 1. Now, what are they trying to do here? So how all they've done is basically, see this term here? What they've done is they basically factorize 2 to the power of n from these two. Actually, factorize 2 to the power of n from this term and this term, right? Let's go there. So if I take out 2 to the power of n from here, I got n plus 1 from the first term, and minus. Now this is like 2. Remember this guy. This term here is like 2 times 2n, right? So if I factorize 2n out, it becomes just 2. Yeah. And then minus 1, so it's just plus 1 on the back. And then I got it, right? Because 1 minus 2 is minus 1. Exactly what I want to prove. Perfect. which equals 2. N minus 1 plus 1 over N plus 1 tick. How is that? Right, so I'm just going to move this up gently. Yeah. Guys, how do I know to use integration for this? Firstly, well, it tells me the question. But secondly, fractions increasing by 1. And then secondly, how do you react to questions where the fractions are slightly different? Well, you utilize your tools. In this case, we use elimination of the original with 1 subbed in for x and the integrated term. Hopefully that was insightful. So if there's a number getting multiplied that increases, that's differentiation. If there's a number that increases and it's a fraction or divided by, that's integration. Guys, hopefully that was useful. Like I said, give us a like if you can, share it with your friends. I'll see you guys in the next lesson. Thank you.